Hello, everybody, and welcome to another episode of Project Shows of IGLUNA 2020 field campaign. I am Jesus Manuel Muñoz Tejeda. I'm a space technology advisor and systems engineer for IGLUNA ESA Lab activity. And today I have with me P11 Celestial, which is going to have something very interesting to tell us because they have worked very, very hard during this year to revolutionize space communications and especially developing a system to revolutionate how is going to be the space communications in the moon. I have been with the project during the last half an hour, and they have everything ready to put forward an excellent project. So P11, the floor is yours. Good luck.
Hi, everyone. Thank you, Jesus, for giving us the mic. Hello, everyone. My name is Mayank. I am project lead for Project P11 Celestial. We are a team of 6 students from Technical University Berlin, representing Masters in Space Engineering Department. And in this IGLUNA event, we are contributing with antennas and communication system. So basically, we are responsible for providing a wireless link to this lunar habitat demonstrator. So what we have for you, let's see on the presentation. So today the presentation is segregated into two main sections. First, I will give you an overview of the project requirements, and second part mostly concerns with the live demonstration. And let's start with who we are first. So we started this project 2 years ago with a vision to actually enable lunar missions for small satellites as small as CubeSats, so that even students like us could do a moon mission. And for this, we came with a project where we had a vision to deploy a lunar relay constellation. We plan to develop 3 satellites which will have these communication systems and antennas that we want to focus on and we want to develop, would enable this communication lunar infrastructure, and would bring out basically the threshold for the lunar missions for future academics, research, space agencies, you name it. And for this, we also worked out on our own link budgets, where we estimated what kind of ground stations we will need, the antenna, the dimensions, and everything. So all of this has been worked out, and this is our vision that we want to achieve in the next decade. The problem statement. Now we do not develop satellites. We focus on development of communication systems and antennas, which would be the core of this constellation that will go to the moon. The problem actually lies with the communication system in our view, is that they are hardwired, which means once you deploy the satellite, it is responsible for functioning only at that frequency with that system and signal processing schemes, which means you cannot reuse it for another mission, and you have to deploy and launch a different satellite for any other mission. Now we want to enable satellite reusability. We think after reusing rockets, now is the time to reuse satellites, where we are answering one core problem of this satellite reusability problem. There are many challenges to it, but one core challenge is the adjustability of the communication systems. And this is where our system that we will demonstrate today, you will see, can be controlled on various modulation, frequency, and other schemes that is required when you have a mission in the orbit, and you can control it, change its communication parameters, and apply it to a different mission altogether without developing a satellite, without launching a satellite, saving a lot of money, time, and resources. For enabling this, we did use state-of-the-art software-defined radios, which is one. Second is additive manufacturing. So these are 2 state-of-the-art technologies that has been enabled into this project to bring out the best performance of the system. In IGLUNA, we have a problem statement that we want to demonstrate a software-defined radio system, and using customized, additively manufactured antennas, we want to demonstrate this system which can be remotely reconfigured. For this, the objectives for our mission are that we want to reach technology readiness level 3 from technology readiness level 1. Our communication system should work on software-defined radio as a microcontroller. We want to improve the system by reducing the input power, but improving and integrating high performance or high gain antennas in there. So we want to strengthen the antenna using the hardware advantage, but not the power advantage. And the final part, it should be reconfigurable, which is very important for satellite reusability, as I explained. And the system should be able to deliver us 1 Mbps right now, but we are targeting with 3 and 10 Mbps in the future as well. This is the overall team. So myself at the first, then I have my alternative team leader, Johannes. Tushar, you see, is on the 3rd position here. Then Guhan next to me. Ravneet worked on antenna systems and Udit worked on system testing. We are supported by our professor, who is also the chair of space technology at Technical University Berlin, Professor Dr. Klaus Bries, our technology supervisor, Dr. Zizong Yun, who has guided us in this technology, and Chem and Manuel are our mentors in the space department. We got external support from Luna, Apostolos, and Jagdish is here, who has joined us today for the presentation. So what we present these three systems. We have developed our own antennas, which we have tested also. You will see in the test videos. We have designed our own RF front end, and we have worked on the firmware to enable this communication system. On the bottom, you see is the fully integrated system with antenna, RF front end, and software in the Raspberry Pi. This will be explained further in the next slides. So the requirements. Just to explain about the project and success criteria, we segregated our project into multiple success criteria. First of all, the antenna design and simulation and testing constitutes for 15% of success of the project, which has been achieved very well. You will see in the next slides. Designing of the RF front end, integrating and testing the hardware altogether constitutes another 35% of success criteria. This is also video recorded and you will see in the test videos today. Then we designed our own firmware and we tested the fully integrated system with hardware and firmware together. This constitutes another additional 30% of the success criteria. So overall, when I stand here with my team, we have achieved 70% of the success criteria. And now today, when we do the demonstration and you will see that we control the system, this will be our last 30% and we will achieve our 100% success criteria. Fingers crossed, right? All right. Then overall project requirements, what are we targeting and what we achieved, we highlighted in this slide for you. We wanted to go with communication system, which is highlighted on the left-hand side of the slide. And here we were able to do a communication system on two different frequencies, 2360, 2361, which will be shifted in the test and using different modulation schemes. So yes, we were able to achieve these two parameters. Frequency regulation was achieved and both the frequencies are in S parameters. So we are able to demonstrate using a software-defined radio, a remotely configured system. On the antenna side, we designed our own patch antenna. We manufactured it. It is with 1U form factor. So 98 mm by 98 is the maximum size of the antenna. And still, this also works on two different frequencies. So it's dual frequency antenna. And it has a weight of 100 grams only. And the gain is 7.4. Although we wanted to go with additive manufacturing because of the lockdowns and other challenges, we could not go for additive manufacturing. Using conventional manufacturing methods, also we were able to achieve the required 7+7 gain. So we have successfully achieved all our requirements as far as the main requirements of the projects are concerned. Now we go to the project show. In the project show, we have highlighted what we designed, what we took off the shelf, and what is basically our contribution to the project. On the left-hand side, we have segregated the 4 subsystems of the communication system as far as hardware is concerned. We took off the shelf a software-defined radio and a Raspberry Pi. And we have integrated this to our in-house developed antennas and communication RF front end. And together, this makes the entire hardware. So we will test antenna and RF front end today. On the right-hand side is the software that we designed ourselves. And my team over here designed this using digital components, which can be reconfigured using modulation schemes, filters, signal formatting schemes, and various other lot of coding that went behind this to actually enable this firmware and do reconfigurations. Now I will hand over this presentation to my external support, Jagdish, who will explain about the antennas and its test demonstration. Jagdish.
Thank you, Mayank. Hello, everyone. Here in the current illustrated slide, we would like to introduce our state-of-the-art antenna, one of the key element of the project. On the left-hand side is the graphs which were obtained from software simulation. The red graph is the graph that was obtained from software simulation, and the center one green graph is from the spectrum analysis. The test apparatus was supplied from our partner company, Rode and Schwartz, and the system was so agile and so robust. It delivered the exact parameters that we pretended to have from it. The system configuration is about 98 to 98 millimeters in dimension, which is most suitable for small satellites, and the thickness is around 5 millimeters, and which makes it very robust and yet lightweight. in the next, I would like to we can see the short clipping of the test demonstration of the antenna.
So this is the demonstration of a off-the-shelf monopole antenna. On the screen you can see is a GNU radio, which is controlling the SDR, which is in the blue case, and the monopole antenna is in the right upper corner of the image. The lower screen is FPC 1500 spectrum analyzer from Rode and Schwarz, which is recording the signal which is being received from this transmission section. Now it is no signal is being transmitted, but now you will see there is a drop, and this means the signal has been started. On the upper screen you can see the waveform, and the signal strength is basically 10 dBm, and is being received at the spectrum analyzer. This is the demonstration of a patch antenna. The setup is still the same. The upper screen is basically the transmission end, and it is FPC 1500 Rode and Schwarz spectrum analyzer, which is receiving end. There is a monopole antenna on the receiving end, and the patch antenna, which is first prototype of Celestial, is being used to transmit the signal from the transmission end. The SDR is connected. You can see the blinking light, and now the transmission has begun, and you just saw the drop in the signal strength. Since this is a directional antenna, the direction matters, and if we start rotating these directions slowly, as you will see, the signal will start dropping in its strength. Right now it is minus 52 dBm strength, and now the signal is being rotated, the antenna is being rotated, and you will see the signal strength has started increasing, 52, 55, 57. This shows how directivity of the antenna is affecting.
Thank you, Jagdish, for explaining us about the antenna subsystem. And now I'll be explaining about the RF front end that is in-house developed for the IGLUNA project. Here you can see on the screen, we have the top view and the bottom view of the subsystem. The basics of this comes from the link budget that we have developed in the team. And all the parameters were then selected, such as the frequencies and the gain for each and every component was selected. And on the basis of those components, we have finalized the filters, the attenuators, and the other LNAs which are required for delivering the input and the output signal. And here we have a soldered PCB which has two different sections, which the above one is the transmission and the lower one is for the reception. And after this, I'll be explaining about the test bed demonstration over there. In the video, you will be having a look on the system setup, where we have a ground station, or we can say the laptop, which is acting as a ground station. And on the hardware side, we have installed a Lime SDR with this RF front end and an antenna, which will be responsible for transmitting a signal. And on the other side, we have a spectrum analyzer from Rode and Schwarz, which will be receiving the signal. So basically, when the video starts, you will be seeing that there is a noise floor, and there is no particular gain. And as soon as the transmission starts, you can easily see that there is a change from the different values. And have explaining everything, let's watch the other video so that you can be more aware of what I have right now explained. So in the demonstration, I will be explaining you about the developed RF frontend and its testing procedure that is developed for the IGLUNA campaign. Here you can see on the left we have the top view showing all the components attached which are responsible for adding gain to the signal, and on the right we have the bottom view where we have a SMA connector which will be connected to the Lime SDR. Here we have a split screen setup to help you visualize the ongoing testing. On the top we have a computer, or in this case the ground station setup, where GNU radio software is used for transmitting a signal which can be received on the FPC 1500 spectrum analyzer from Rode and Schwarz. In the setup on the ground station, we have a Lime SDR connected to the RF front end, as well as on both the sides of transmission and receiving, we have installed an off-the-shelf monopole antenna. As you would have observed, until the transmission was started, the signal on the spectrum analyzer was constantly near around minus 76 dBm. As the transmission has begun, and as we zoom onto the spectrum analyzer screen, we can see that there is a gain of more than 15 dB of signal power, and the reading is now nearly constant around minus 60 dBm. This shows that the RF front end is working and does not block the signal, but instead adds to the signal strength. although this is not a final product of Celestial, but it shows that it has capabilities, and with some further improvement, the signal strength can be further enhanced.
Thank you, Tushar, for explaining about the RF front end. I am Glenn. I'm explaining about the software development. On the screen, you can see two laptops. The bottom one on the left-hand side is it represents the ground station, and on the top side, in the middle of the screen, you can see the testbed systems. And we did some demonstration for the required change of frequency and change of modulation in the testbed system, and by sending commands from the ground station. And depending on the command received, we changed the frequency and modulation scheme from the testbed system, and was able to receive data from the testbed system to the ground station. This particular test was made in video, and we'll be showing that video, and let's watch the video right now. Thank you. So this is the image of the laptop that represents the ground station. It has Lime SDR with two off-the-shelf monopole antenna attached to it. This is the image of the laptop that represents the testbed system. It has the same setup and configuration as the ground station laptop. Now we have the testbed system on the top and the ground station on the bottom. In the ground station, we can see certain files which are empty, where we'll be getting data from the testbed system. Now we'll be starting the testbed system. Once the testbed system is started, it will go on automation mode. All the tasks will be performed automatically. Now the testbed system has started. Now it's going on the receiving mode to receive data from the ground station. Now we have just transmitted a command from the ground station to the testbed system. As you can see, it received a command 1. So it stopped the receiving mode and will be transmitting a data in 20 seconds. So meanwhile, we are preparing our ground station to receive the data. As you can see, the testbed system has started transmitting the data. Now this data is been sent using OFDM channeling and at the frequency of 2360. And the modulation scheme which is used for this data transmission is QPSK. After 20 seconds, the transmission has been stopped from the testbed system, and in another 20 seconds, it goes back to the receiving mode. Meanwhile, we have prepared our ground station to send the next command to the testbed system. Now the testbed system has gone back to receiving mode, and we just transmitted our second command from the ground station to the testbed system. Now the testbed system has received the command 2. So it stopped the receiving mode and going back to transmission mode. So we are preparing our ground station to receive this data. As you can see, the testbed system has started transmitting data to the ground station. This time, we are using the same modulation scheme as test 1, but with different frequency range. Instead of 2360, in this test scenario, we are using the frequency range of 2361, and we are using the same OFDM channeling. Now the transmission has stopped after 20 seconds. Now after another 20 seconds, the testbed system will go back to receiving mode. Meanwhile, the ground station is ready to give this next command and the final test scenario to the testbed system. The testbed system has gone back to receiving mode. Now the transmission from the ground station has been started, so it has transmitted a command to the testbed system. Testbed system has received the command 3. So it stopped the receiving mode and is going to transmit data to the ground station again. So we have prepared a ground station to receive the data from the testbed system. Yes. Now the transmission has started. This time we are using the same frequency as we had in the test one, which is 2360, and we are using the same channeling method as well, OFDM, but our modulation scheme is different. Instead of QPSK, we are using BPSK modulation scheme. Now the data has been received for 20 seconds, and it has the testbed system has stopped the transmission and going back to receiving mode. As you can see, now we have got data from the testbed system to the ground station using 3 different test scenarios. In all the 3 test scenarios, we have received the same file. With this, we have done all the 3 test scenarios and we have received the data. And we are still working on improving our software developing for the final demonstration. Thank you very much.
Hi. So suddenly I think my team disappeared. I don't think it's time for live demonstration and they're not here. So let me explain you what happens in the live demonstration now. On your screen, you see is a project setup we have. So the lower side is the ground station setup where we put our own patch antennas, as I explained, and is the GNU laptop as a ground station. And we will display a screen from there for audience to understand what is happening on the testbed system and on the ground station. On the upper right corner is basically the lander. It's a moon lander, and we have our communication system that will receive the communication commands. So the scenario is the ground station is being operated by an astronaut from a lunar habitat and is trying to communicate to its lander, trying to get some information. So what is happening on the testbed system? I think Tushar is over there. He will explain you what is the testbed system all about. Over to Tushar.
Thank you, Mayank. So I'm standing at the PTS facility and I'm standing with Alina, the lander. So I have already installed my antennas over here, and at the back end, we have our Raspberry Pi and the other Lime SDR system attached to it. So once we receive a command over here, there will be a communication link, and then the response will be sent back to the ground station accordingly. So this will happen continuously, and then we'll be doing demonstration with Space ID as well. So this is the setup from my side. Over to you, back to you, Mayank.
Yes. Hi. So thank you, Tushar, for explaining the testbed setup. I am here. I found Gohan. He was behind the ground station. So now Gohan, explain us what is happening on the ground station. What is the setup? How he will control the system over the testbed system. So Gohan, please explain us what is happening here.
Let me share my screen. Okay. Now everyone can see the desktop over here, and over here we can see on the left hand side you can see the GUI which control the ground station. Over here we have the frequency and the modulation scheme which we can choose between, and using these 2 buttons we can either transmit data or receive data. And if you want to send any data command to it, we just write the command over here and we can write it, and we can transmit it from the ground station. And right hand side you can see the test, and once it start from here I can start the system. Once it started, it goes to the automate mode, and depends on the commands we send from the ground station, it can change this frequency, change this modulation, and send data depending on what frequency modulation we want.
Okay, so basically the left hand side, which is the pink window, is the basically ground station. Yeah. So, and you are using graphical user interface for audience to understand what is happening and what is the frequency being transmitted and what is the modulation scheme being transmitted. On the right hand side, it's more or less a system backend and is being projected, I guess, and right is what we are doing and happening on the testbed system. So as to visualize what is happening over there, and this will be automated, right?
Yes.
All right, great. Then can we start the test already? Yep. All right. Then we start the test. Okay, so now you see the system on the testbed setup has come to the receiving mode and is expecting a command need to be delivered from the ground station. And the ground station over here, TX button has been transmitted and the command will now go from the testbed system and is received with the 4 dots over there, which you see is a 2. The system shows that receiving command is 2. So 2 command transmitted and system is recognizing it, readjusting it, and in the meanwhile we are readjusting our ground station to receive the signal from the test system on the same configuration. Now ground station is basically expecting it, and you see the 4 dots. This means it's temperature modulation scheme, so QBPS and QPSK, and this is going to continue for 20 seconds so as to everybody can visualize that right now system is working on the frequency of 2360 and QPS modulation scheme. Now the system is going back again to the reception mode, in which it expects the ground station to send another command for the reconfiguration, and the system is ready to receive another command on the lender, and the ground station has transmitted another command, and the command is received 3, which is the third command, and the system has stopped and is now readjusting itself to actually new is now 2360 and BPSK scheme. And now the system on the test bed, the right hand side, is transmitting and the ground station is ready to receive. Now, since this is BPSK, it is binary, so 2 dots are visible and the modulation scheme has been updated, which means that we were able to reconfigure the system remotely without changing any hardware on it to a new modulation scheme. And this is one parameter of readjustment. Now, the ground station will send another command and the system on the test bed comes to another reception mode, expecting a new command that needs to be delivered. So you will see the graphs appearing on the right hand side. So here and system, and right now all this is noise, but now since the command is delivered, you will see system showing that command received 0. So 0 command is gone, and we are resetting the ground station to now 2361 and BPSK. So modulation scheme and the frequency both are changed in this command, and this is where you will see that we were able to change multiple parameters in one command as well. So system is highly reconfigurable, and we are receiving the same data as well. So system got reconfigured in this meantime, and we were able to change the setting on the ground station to receive this command. Now, these are the type of changes that we expect from the future communication systems, both for space applications and for deep space applications, which do not need hardware changes, but which can be reconfigured, robust system, and can adjust with the operation modes that are being connected over there. Now, the system is coming for the final command, which is setting itself this command, and the ground station has transmitted its final command again. This being see now received command 1. So we have received this command as well, and the system will reset itself. Now the modulation scheme is again changed to QPSK. We will see 4 dots that should appear when we receive this on the ground station. All this haziness that you see in the lower graph before we receive anything is basically because of the noise that signal is not received. But when they become really dense dots, that means signal is being received. Or when it's SK to its BPSK. There are many modulation schemes. This can even 16, 64, whatever. But right now, this is just 2 that we wanted to demonstrate only. So we were able to demonstrate, and it's a successful demonstration. Let's move up. So project is now more than 70% successful. Okay, then now we will go to our collaboration demonstration. Here we have Mr. Laurie Kimmel from Space IT CTO, who is sitting in Estonia here, and I will hand over to explain about his participation in the project and what is the collaboration that is about to happen. So, Laurie, over to you, please.
Hello, everyone. I'm Lauri Kimmel from SpaceIT, and now I will demonstrate to you how we receive live data from testbed. Can I share my screen? Thank you very much. This is our cloud-based mission control system, and this is the dashboard we created for the testbed. Here we see data from the testbed coming through the ground station and received in our cloud-based MCS. Next, I'll show you the raw data which we are receiving. And lastly, I'd like to show you how this data is actually changing over the time. So as you can see, it has been quite stable, but there are some spikes and gaps here and there. So to conclude my part, I'd like to say it has been great pleasure to work with Celestial and the IGLUNA team, and thank you for the opportunity. Spaceit over and out.
Laurie, can you please just go back to the time schedules? I just to highlight that how these time schedules are changing over that is received, which you were just showing previously. The time steps when the signal is
yes. So as you can see, the blue values are live data, and timestamps under the blue values are updated in real time, and we can visualize this in raw values screen as well. So as you can see, timestamps are updated as live data is received at our end. Thank you.
Thank you very much. So great. And now this is 100% success, right? Yeah, we are 100% success. So now we'll get back to the presentation, and we will show you about the next steps, basically ramp up and what is happening. So I will hand it over to my colleague Johannes, who will explain you about the next steps in the next slides. Basically.
Hello, everybody. This is Johannes. This is Joe, joining from the Celestial office in Nuremberg. I'm also happy to be here. Thanks to all the visitors who are watching at the moment. And I want to take a few more moments to talk about the project and our partners, especially starting with Spaceit. We just saw how Laurie explained how Spaceit is helping our demonstration today. And I want to highlight again the benefits that Spaceit software, Spaceit solution is providing to our demonstration today and to the space industry in general. Because what they're actually providing is a mission control as a service, which allows their users to access many ground stations on this planet via their cloud-based software. And with that, handle commands, handle satellite telemetry and payload data. And also their solution is offering many more supporting tools and services, like, for example, the data visualization, which we also saw in just a minute ago in our demonstration. So, and this solution is really great because the advantages for the users with this end-to-end infrastructure is really a seamless integration of ground stations across this planet, various ground stations, which allows the users to focus on their mission and not handle the ground station too much. And also the availability is significantly increased because of the big network that Spaceit has. It's right now at 300 plus ground stations and still growing. So overall, their access, their ground station access is also remote, which can be done which can be accessed from any desktop and even mobile devices, which is especially beneficial now in the new economy and the new work environment we are living post the pandemic. So, and besides Spaceit, we have more additional partners on our next slide, which are both academic and industrial. In this point, we want to sincerely thank all our partners, especially TU Berlin, our home university, and the Master of Space Engineering program, which the engineering team is all part of, and also University of Würzburg, which we have been and looking to collaborate on the software development. But also we have many industrial partners actually for various different aspects of the project. Initiative for the Industrial Innovators has helped us with the funding of our first prototype. But then there's TruRC from Canada, who has been a great development support for us for the antenna. The same is true for ST Engineering, which helped us for the antenna development, but also communication system development, as well as OHB. And Roda and Schwarz has been great for helping us in testing. And now we're looking forward to do manufacturing actually with Neotech here in Nuremberg. So the next steps for us is our ramp up. And actually overall to say about this, IGLUNA 2020 has been a great experience and has been a big and important milestone for us. And we are already looking ahead, because now we want to take it to the next step. We want to take this higher than an academic project and make this an industrial and commercial project. And for this, we've been working on our ramp-up plans. And to make this industrial, first of all, obviously, we need funding. We're looking for 750,000 euro, and this will cover everything, the research and development to further improve our prototypes, to test them, to bring them to the orbit, to do in-orbit demonstration, and to bring them to the market. The antenna is supposed to go to the market this year in fall, and the communication system as early as next year in the spring. So we've cherished all the expert feedbacks across our development, and we continue to look for more expert feedback to challenge our thinking and to improve our designs. As mentioned, we want to take the project to the next level. IGLUNA was a relevant simulated environment. Now we want to go for the actual relevant environment in space to demonstrate our technology. We mentioned our partners, and this has been a great help for us, and we hope we can keep those partners and now convert them to industrial partnerships looking forward. And also facilities will be important for us looking ahead. So finally, I want to say a few things for the in-orbit demonstration. We're looking to do this year for the antenna, next year for the communication system, and as also mentioned, the product launch for both systems this and next year. And finally, we will also be part of IGLUNA 2020. We've been robbed this year of the physical field campaign, unfortunately, but next year we hope everything will be physical and we actually can go to the Alps in Switzerland. And Celestial will be there doing a space communication workshop for all the participants. So that's it from my side. Thank you for the visitors, and back to you, Mayank.
Thank you very much, Joe. Was very insightful. So now I would just go to basically my second last slide. What were the lessons learned? In every project, there are lessons learned. One of the biggest lessons came to us was with documentation. Documentation basically cleared us. The documentations were done with ECSS standards, and this cleared us a lot of things about the project that were very minute but very critical and could be easily ignored. So documentation is always important. This is what we also convey to the future IGLUNA teams and to the other project teams who are watching us. Please stay focused on documentation, presentation, and reports. The project management. So having a standard platform to communicate goes a long way. This helps clearing a lot of doubts. Actually, some people who are not even concerned with the topic may need to know this information to work more efficiently. And the one of the biggest learning was with Swiss Space Center. We were very open, we were very vocal about our challenges, and on the same time we were very proactive on solving them by ourselves. And getting help from Swiss Space Center actually sorted out a lot of big things for us. For example, we were about talking to Baycom to acquiring the frequencies in Switzerland which we want to communicate on. This is where this help comes. So be vocal about your challenges and the problems that you face. Don't try to face them alone. And with the project team, when you have the neighboring project teams, this is to support you. It's not a competition. You need to focus on read their documentation, try to analyze their requirements and objectives, and maybe you can help them achieve them. Go for collaborations. This is what we did. This is why we have now Space IT working with us in collaboration, and we were able to demonstrate an inter-collaboration live demonstration, which is also very, very challenging. So be open to ideas and try to explore more. And just one more thing, this is also our one last big announcement that we want to make. So we have registered ourselves now as an official company. So we are Celestial Space Technologies GmbH on this. Yeah, so so we are a company now, and this is our official website. Please visit us. It's still in making, but there are some information that you can already find, especially the contact information. I also want to briefly go over a little bit 3 or 4 very key milestones that happened to our journey right now. So we started in 2018 in a hackathon. Then last year we won InnoSpace Masters Award. We were 3rd. And then in 2020 now we are doing the IGLUNA field campaign. We are coming up with our first functional prototypes and MVPs, minimum viable products. And 2 months ago, we got selected into ESA BIC officially, and we have registered ourselves as a company. Now we are Celestial, and we are moving very fast towards the moon. This is our contact details, and thank you. And now we are open for the questions from the audience. Thank you very much.
Thank you very much, Mayank. It's been really, really impressive. And we really appreciate that you took the risk actually to test your technology in a live demonstration, because it's something that is really risky, but we really saw that your technology is working, that you have a functional prototype, and even with the technical difficulties that we all had throughout this year, you managed to put it forward. So hats off, congratulations. It's been amazing, and I've seen that the audience is actually congratulating you from their side as well. So yeah, it's been fantastic. And now I'm gonna start making the Q&A and going through all the comments. I have separated into some more technical questions that I will start asking to you, and then we will go a little bit to the business side, if this is all right from your side. So the first one I came up with is about your system itself. What is your system different from the actual state of the art of those kind of space communication systems? You talk about additive manufacturing, you talk about frequency regulation. So if somebody wants to take your technology, what will be the headline that you will say to them in order to purchase this and not the competence that is you are competing with?
Yes, thank you for the question. I think this question is very important to highlight here. When we are developing this technology, there are few USPs, few unique points that we wanted to design about this. So I will start with the antennas first. The antennas that we are currently manufacturing or we are currently designing, they are designed to work over multiple frequencies, not just one frequency. So it's multiple frequency antenna that we are focusing on, not just having large bandwidth, but multiple frequencies itself, and then having large bandwidth to these frequencies. So this is one unique thing which I haven't come across in a lot of products already available online, even off the shelf. So this is a big advantage where I say satellite reusability is required, because if you have an antenna that complements these all the frequencies, you are basically able to then communicate using the same antenna. Antenna is also very important part for answering the communication reusability question, because if your communication system can withstand these multiple frequencies but your antenna cannot, basically it's a full stop. You cannot go beyond that, and your technology is of no importance to the project for reusability. So antenna is supporting our entire vision in this way, that it can be reconfigured. In the further steps, we also want to take this to next steps, which is array or flat panel antennas. This will be where we can actually go to the moon, and in the moon we don't need satellites that has this rotors, to rotate antennas. We need stable antennas who can steer beam their communication signals, and this is where these antennas who can work on multiple frequencies, can do beam steering, will come in very handy, because your satellite will not have any jerks or mechanical systems moving in there, and your satellite will be very stable, your rovers will be stable, your landers will be stable. So this is a huge advantage that will go a long way for moon projects, for space projects, for all these satellites that we are designing. Coming to our communication system, it is software defined radio. There are many systems. There are few systems that we outlined. They're available already. But in this part also, we are designing the system that actually goes into next step, where it will have multiple channeling, which means that our system would be able to communicate to multiple projects at the same time on different processing schemes. This will be very unique, especially for a relay satellite that we are trying to plan, because then relay satellite could communicate to rover, to lander, and to an orbiter on the moon at the same time, using different modulation scheme, different frequency schemes. So same satellite is working with everybody on their customized requirement and providing the best quality service to these missions. Yeah. That would be the answer. Yeah.
Absolutely. Thank you very much, Mayank. And actually, we can see that your technology is actually game-changing for the space communications. I had just a small comment. When you were talking about the different frequencies and the different bandwidth that you want to tell and you want to implement, can you put some numbers already? How many frequencies can we choose from? How big is the bandwidth you are aiming for?
Yeah. So right now with our antenna, I would say we are targeting already 300 plus megahertz that we should be able to deliver, which is the highest I have ever seen in studying all these antennas. Secondly, the frequencies. So frequency will not have a range. Basically, from 2 to 3 gigahertz, you can switch. We will try to provide a range in which you can work, and the limitation factor would be the end. because antenna can work on all these frequencies, but it will still have very key frequencies that it work with maximum efficiency without having back current coming to the system and destroying it. So this will be the limiting factor, antenna. But on the other side, the communication system right now, what we have can already work till 5 gigahertz from the off the shelf that we took, and we can reconfigure this to any frequency while designing the firmware. So this again comes back to the firmware part, and communication system does not have limitation on this, but the antennas will have some kind of limitations on this. Yeah.
Thank you very much, Mayank. Glad to hear those great news. Actually, I'm very happy to say that your system is flexible, that can be optimized to different frequencies. Your bandwidth is really, really impressive. You were also talking about the differences in the type of antennas that you want to implement, that you were aiming for a different time afterwards. But right now you have a patch antenna. So why did you choose a patch antenna, not any other kind of antenna? The question comes from the audience.
All right. So why patch antenna? Yeah, it's a good question. Actually, we also planned to have helix antenna, other antennas. We were very ambitious, but then we came to senses. Now the patch antenna. Why patch antenna out of all? So the patch antenna, two reasons. First of all, we started that we wanted to have enable academic missions, which are CubeSat missions. And these CubeSat missions generally go with patch antennas because they work on this S-band frequency range very good. And it's easy to implement in the CubeSat than helix antenna and any other kind of antenna. So this was one reason to select the patch antenna. Secondly, as I said, we are envisioning flat panel array antennas. And in this flat panel array antenna, patch antenna would be one element that can be repeated for number of times in an array to make this flat panel array antennas. And this is where we want to go with the patch antenna. Right now, the patch antenna that you see is one element that we are perfecting it on its frequency, on its performance. And then this will be repeated on a bigger, large scale panel that we are able to give very optimum performance in the patch antennas or flat panel array antennas. And antennas do not just have application only in space. Antennas have application everywhere, probably. Right now, the audience who are watching us, they are using one antenna basically to communicate with us. So antennas are everywhere around us, and we are trying to optimize these antennas, and this will have a lot of applications as I see it. Thank you.
Yes, absolutely. And actually, from the audience, I had a funny question that they are asking about some of the applications of your system. And you're telling me you can run Crisis. Crisis is a video game. So I guess the question, in fact, means with your current power system that you have, what are the limited technologies data that you can send from point to point? We saw there are text commands, but how much you can improve it so you can send photos, videos, and some multimedia stuff.
So if you talk about the antennas, the limitation comes from the bandwidth. The more the bandwidth, the more is the throughput of the antenna, and the better you can transmit. So we are trying to go with maximum bandwidth that we can give, which is, I said, 300 plus. We already have achieved this in one of our designs, and we are improving this. So it also depends on the materials that we work on and the designs we design. So we are also trying to go into the material sections. We don't want to use the traditional materials that are being used already. We want to do our own R&D in the materials for antennas, and we want to manufacture these. But answering your question, for gaming industry and for having these antennas working with high throughput videos, live videos, or real time, I think there will come the question with we can achieve this having a panel. For example, 4 array antenna. We don't use one antenna. We use 4 antennas altogether. This will exponentially enhance the bandwidth. It will exponentially enhance the frequencies and the throughput of the antenna. The antennas are generally very much improved when you have multiple arrays in there. This is the advantage of using array antenna, because you have multiple antennas looking at it. And this is where we will target. So we want to target, or when we target, for example, gaming industry, or so to say, a project with real-time communications, we will then actually go into this direction, these array antennas with 4, 6, 8, 12 elements, and then making it high throughput antennas as required by the project or by the customers, for example.
Absolutely, absolutely. And I think this is a very good point to go to the business section, that now that you were talking about different applications that we can actually use nowadays. So your system is actually aiming for a moon constellation, but right now, as there is no business on the moon, I guess you want to focus on an Earth application. So I guess it's a very good time to tell now what are the benefits that Celestial can provide to the Earth business.
Yeah, for Earth business, actually, we were asked the question many times actually, and we were also told that you should focus on the already existing market. Moon market does not exist yet, and you should focus on the existing market, which is space market. And yes, we have solutions for this. And this is what I also highlighted in one of our slide, that already existing systems are mostly hardwired, especially for this system. So we are targeting constellations which have 25 to 30 satellites going up, or individual systems which do not really specifically develop their own communication systems and antennas, and which believe in integration of the shelf communication systems and antennas, and we want to be providers for this. There are many constellations going up there, smaller ones for different applications. For example, there are constellation from Switzerland itself, and you from Swiss Space Center will know it better. There is Astrocast, which is going up there with and Clean Space is going up there with constellations. So there are many constellations coming up, and we are targeting this kind of customers who will have these small satellites, not large in number, but yet they need high performance in these small sector. So this is one sector that is in our view, and we are going for it right now. But coming to other applications, these antennas will have applications, for example, in IoT. IoT is already big, and people are looking for these communication devices and antennas in IoT. And this would be our another application sector, which is non-space sector, and we will target this. We are also envisioning moving into and applying these antennas into logistics, for example, which needs regular monitoring of the transportation, seaways and roadways and airways sticks, where they want to target and want to, customers want to know where their shipment is right now, and it's in the sea somewhere, and they want to locate where they are. And these kind of antennas would go a long way for logistics as well. So there are many areas, space and non-space, for antennas and for the communication system that we can target. Even, for example, the space tourism, or so to say the civil tourism or aircrafts which are going where people have the problem of getting Wi-Fi on the airplane. We can put this system which can connect to these mega constellations from SpaceX, or for one whichever goes first, and our system and patch antennas can connect to these mega constellation and provide a Wi-Fi to these civil aircrafts and passengers and tourists going in these flights. This is also big market. This can be targeted very easily with the system we are developing. Yeah.
Absolutely, and we can see that you have a very clear business model for your technology, which is something very, very important when you are starting your own business. And we are very happy from the IGLUNA side that we help you out to develop your technology and make it a startup. So congratulations. And I have people asking already from the audience if your technology has a price. Have you settled a cost for your technology? Can you tell us more about that?
So next step for us in big way is, as Joe said, we are going for product launch, and we are already very close with finalizing antenna now. Patch antenna offering maximum bandwidth and other various parameters. And we will be launching this targeted September this year, and then we are targeting a moon mission by the end of this year for this patch antenna. With communication system, this is our first function prototype has come into picture. So this is probably TRL level 2. One would take another a year and a half to actually get into the testing phase of a full scale communication system. And we are looking that we are able to launch this next year into the orbit and already put these products in the market. So these are two big things going up for us now. And as I said, we want to move ahead into array antennas. This is also a big market for us. We on the side will look for IoT applications and other applications that we want to do. But as far as technology is concerned, the big thing for us is launching a product this year and the communication system next year. Yeah.
Added to the Mayank's answer, we are also looking for R&D in additive manufacturing, advanced functional materials, and which makes the system more lightweight and much more stronger to withstand higher temperatures, vibrations, and much more to face much more harsh environment where the antennas can be used, and also where the space is limited and we need to use more power for the transmission of signals. We can still yeah, adjust the antennas which we are already having, because we have already seen pretty good results from the first iteration itself. So we'll be coming up with new iterations with much more advanced material and less cost.
Just one more thing to add over here. We are also working on the antenna enhancement technique by going into deep research for this. as well as like implementing different circuits. Let's say I'll just give you a few examples. Let's say short circuiting the ground plane with the patch, and different other parameters can be implemented, applying a capacitance circuit, applying a resistance circuit, so that the antenna performance is enhanced, and we don't have to go much with the bigger antennas. We can also have smaller antennas, and with these enhancement techniques, we can also improve the quality of service.
Yeah, thank you.
Absolutely, thank you very much. It's been a really, really complete answer. And we really hope to see your technology in the market in the short future. I have with me 4 more minutes, so I'm going to target the last 2 questions of today. The first one, I think it will be more target for the general public, just to have a headline of your technology, because they are asking if you, for example, can have a lunar GPS system with your technology. So basically, with all your potential, do you really think you could have a lunar GPS system using your technology in the short future if you, for example, succeed on the launch?
So lunar GPS, we have not yet looked into this time. We are looking in this direction at this time, but having a communication relay network, and there are satellites who are communication navigational satellites, and when we go into designing of the satellites in the future, then definitely this is one of our targeted application if we can explore this. But for now, I would just say we have not yet looked into this, but this I don't expect it to be very different than what we already.
Exactly, and I think that in the next future you can target different markets, because they were also asking about wireless power transmission, so basically transmitting power from one receptor to one emitter. I think this is already a new technology that you could implement in the future, and we are really looking forward to that. And my last question actually related to your background, where you are right now. You are in PTS and power transportation systems. What is your relationship with planetary transportation systems? Are they going to provide the lander? Are you going to launch with them?
So yeah, for that, I think maybe Robert, as founder for PTS, can already answer this for us. I'm already giving it.
Hello, hi. Yeah, welcome to our small facility here. No, we're just basically happy to help, and we're really excited about the moon, and we totally believe in the lunar economy and market. So I think it's really good that Celestial focuses on the earthbound applications like we also now did. But I totally see why they're going for the moon, and we will help them as best as we can.
All right. So yeah.
Thank you very much. Glad to see that the planetary transportation system is also one of your partners. We had actually a talk with them a few days back, so we will put it in the description here. And with that, I would like to conclude this session. I would like to thank P11 Celestia for this awesome presentation, also for PTS to letting the facilities to them to set up and provide the testbed for the technology. So thank you very much.
Yeah, just one minute if we can get. I would just like to invite entire team that helped us on the screen, and last picture that ends up with everybody in the screen. Come, everybody. Yeah, come.
Let's see all your team together.
Yeah, maybe I can just sit here, you know, like maybe, yeah. All right. So yeah, this is the entire team that was behind this, helping us, and thank you.
Thank you very much, Mayank, and we hope that in a few years, all the people that will be working with you will fit in that picture. So thank you very much, everybody, and I will see you in the next show today after lunch. Bye-bye.